Hello, my name is Jacob Dine, and today I'm going to talk about Lab 5 for Physics 2212. So our main goal of this experiment is to examine and understand the dynamics of a descending magnet through an aluminum tube in the context of Faraday's law. For observations, we have that our predicted time that the magnet will fall is 0.6 seconds, and the actual time taken to fall was 0.75. Our starting point was, we know that resistance is negligible. The system are the magnet and the aluminum tube, and everything else is the surroundings. The baseline is basically the setup of the magnet and tube as stated in the instructions. So for this lab, there were not too many key concepts. We have the principle of electromagnetic induction, which is Faraday's law, which basically equals the change in magnetic flux over time times the number of loops. We also have the magnetic field calculations with the Weis-Howard law for magnetic loop as well. Also have the dynamics and motion for Newton's law of motion, second and third law. And we also have that the electrical current and potential difference relationship, aka Ohm's law, which is the current equals the voltage divided by resistance. So for the experiment, we have our descending magnet, the environmental context, basically interaction with the Earth's gravitational field, and the aluminum foil cylinder. Our methodology is that basically we're going to identify the magnetic north pole through a designated application, and then measure its mass. Then ascertain the cylinder inner diameter and its length, as well as the thickness of the aluminum foil. Then we're going to conduct a series of 5 trials where the magnet is allowed to fall through the aluminum foil cylinder. And then we're going to monitor and document the duration of the magnet to pass completely through the cylinder in each trial. So yeah, this is basically a 5-second video of me dropping the magnet through the aluminum tube for you guys to see how slowly it falls in one of the trials. So basically, after 5 trials, we have our 5 attempts with 5 different times. Of course, our average was 0.7 seconds. So for physical parameters of the cylinder, we have its internal diameter, its length, the aluminum foil thickness, and the overall cylinder dimensions. We basically only have its total diameter. And the magnet specification, we have its mass that it was 0.025 kilograms. So for our computational model, we're first going to initialize our physical constants. We're going to use for our formulas, and then we're going to create the tube of aluminum foil, and then we're just going to create the magnet as well for visualization. So next in our computational model, we're just going to visualize the bar magnet as it falls, and then we're going to create a function to calculate the magnetic field of the bar magnet. Okay, first we basically calculate the magnetic field using our distance, magnitude, and unit vector position, and we just calculate B later. Then we're just going to create a function to calculate the magnetic flux. First we calculate the radius of the ring, the distance, and the speed the magnet falls, and then we're just going to calculate the change in flux. Okay, and then we're just going to simulate the loop of how the magnet falls through every loop of the tube. Okay, and then we're just going to calculate the gravitational force of the magnet. Okay, and then we're just going to calculate the net force on the magnet to basically know how long it takes and for it to simulate the correct way. And then basically at the end, we're just going to update the magnetic velocity and position. So first for our results, we can see with the magnetic dipole moment is set at 3.71, and as determined in lab 3, the simulation resulted in the magnetic taking 2.214 seconds to pass through the tube, which is inconsistent with the laboratory findings. Also for our second results, we have also with the magnetic dipole moment set at 245, okay, as determined in the lab. This simulation resulted in the magnet taking around 2.5 seconds to pass through the tube, which is also inconsistent with what I found in the laboratory. So to discuss my potential sources of error, basically it's the inaccuracy in length measurements I obtained using the meter stick. Also the interaction involving friction between the magnet and the interior of the tube could have affected the results. As you can see in the video, the magnet actually sticks to the carton in the interior of the tube. Also a hypothetical scenario and their implications basically, should the conductor resistivity be minimized to near 0, it would alter the magnetic descent. As resistivity approaches 0, which is akin to eliminating resistance, Ohm's law suggests a substantial current would result, exerting a stronger magnetic force, consequently slowing down the magnet fall. So to finish, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of a falling magnet change? So resistance and current are inversely proportional, as I said in the formula at the beginning. If the resistivity decreased to as close as possible to 0, then our current will be extremely high and cause the magnet to fall extremely slowly within the tube. Also, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So If there were holes in or slots in the tube, there would be less current rings within the tube itself. Therefore, with less overcurrent rings, there will be less opposing force within the tube, and thus the magnet will fall faster within the tube. This totally makes sense according to the law. Okay, and this would result in a shorter period of time where the magnet is falling within the tube. Thank you very much.